Okay, fairly simple to see as we did before, to draw the Lewis structure for binary molecules, for covalent molecules. What happens when I have three or four or five different elements and they're covalently bonding to one another? What do I do then? I mean, let's say I have this thing SCl2, so I have three atoms here. I have one S and two Cls, and they all want to hang out, and they're all sharing things, and this gets a little hairy pretty quickly. So how do we do that? So there is certainly a recipe that if you follow this each time, you will get it right. And we're gonna go through about 100,000 examples from now until the end of these. So you will hopefully get more and more comfortable with this. So first step to do this, you don't start with Lewis dot diagrams right away. You don't. First thing you do is you calculate the total number of valence electrons you have. All right. And I will show you an example where you have charges for ions. But here I don't have an ion, so don't worry about this step. Okay, but do recall this step. It will come up. It will certainly come up. So right now I have no ion, so I ignore this. S has 6, Cl has 7, and so altogether I have 20 because I have 2 Cl's and 1 S. So that means I have to have 20 valence electrons, and I have to organize them around 3 atoms. Okay. Identify the central atom. Well, what do we mean by that? When we had this stuff before here, there's no central atom. There are just 2 of them. So that was pretty easy. You just kind of smush them together. Here, I need to identify, I have S and 2 Cl's, so I have to identify who's going to be in the middle. So usually when I have something like this, the two like atoms stay away from one another, actually. And the one that's unlike the others is usually the central one. So I'm going to put S in the middle and put Cl's in the wings. Okay, so I'll write this as a skeletal structure. Now I'm going to give electrons to the wings first, so that they all have 8. That's the first thing I'm doing. So I have 20, so I can give 8 to this and 8 to this, all right? So this has 8, this has 8, so the Cls are happy. The Cls are very happy, they have their own octet. And I give away 16. So I have 4 left. Okay, so number 4, I have 4 left. Distribute the 4 that are left on the central atom. So I'll put 2 here, and so now I can write this. Replace any pairs with a bond, and I get this. Okay. Step 5, which we're not doing here. If the central atom does not have 8, right, that means I have to do trial and error. If I get to a point where, let's say Cl only had 6, then I have to have multiple bonds. Then I redo this to try to make S happy. So if let's say I were to move this over here, the Cl would still have 8, right? So that means I need to kind of reiterate. So I don't have to iterate here. This is good. This is what SCl2 looks like. Let's look at other examples. Okay, let's look at COCl2. All right. Okay, so let's take the total number of valence electrons, and this is not an ionic type thing, so I don't have to add charges. C has 4, Cl has 7, and O has 6. So for a total of 4 from the carbon, 14 from the 2 chlorines, and 6 from the oxygen. I have 24 to distribute. Okay, now I have to identify the central atom. I will give you another type thing to kind of know easily. Carbon tends to be the central atom. So whenever you have carbon around, it's going to be the central atom. All right. So I'm going to put carbon in the middle and Cl, Cl, and O like that. Okay, and I wrote here C is usually the central atom. Okay, now I'm going to give 8 to each one of the ones in the peripheries. So Cl is going to get 8, O is going to get 8, Cl is going to get 8. Okay, so I'm going to distribute that, and it's going to look like that. All right. So that looks good, right? So they have 8, 8, and 8, so they're happy. They don't care. They're happy. Distribute the remaining electrons to the central atom, but I already gave all 24 away, so I have none to give to the C, and the C is not happy. The C only has 6. So that means to me that there's multiple bonds. So I have to reiterate this, or not just really reiterate. I'm just going to move these 2 electrons and put them here. Okay, if I do that, it will look like this. If I move these 2 over, well, I guess in this particular example, I move these 2 over. Now they get erased. And I put them here. So that's what happening. It's happening here. Carbon, as I'm circling around it, has 8. So it is happy. Oxygen also has 8. So it is happy. Chlorine has 8. And chlorine is 8. Everyone's got 8. Everyone's got the octet. Everyone's happy. And so I actually have a double bond between the C and the O. Okay, so that's how you would iterate when the central atom does not have the 8 you want. Okay, let's look at these things called formal charges. All right, so sometimes I can draw two structures that look similar. That look to satisfy what we did. So you might ask yourself here. So I'm gonna actually go here and show you. Because I don't want to get, so I can actually get a double bond between the oxygen, sorry, the chlorine and the carbon. I can do this. So what we had written a second ago, that's actually correct, but I'll show you how you'd know. We just wrote this. And I mentioned to you that if you looked at it, I don't know, it's so dark here. Okay, so he's got 8. He's got 8. He's got 8. See that the carbon, in case you're missing it, the carbon has 8. 1, 2, 3, 4, 5, 6, 7, 8. Carbon's happy, and Cl has 8. This Cl has 8. And this oxygen has 8. Everybody's happy. So we wrote that, and we said, sure, let's do that. Why can't we write the top one? I mean, it looks to be right. What's up with that? How do we know that that's incorrect? And so what we'll do is we're going to actually have this thing called a formal charge. So now, from my own experience, I don't have to do that because I know that chlorine never forms double bonds. I just happen to know that. And I think with experience, you get to see that. Chlorine does not form double bonds. Chlorine only needs 1 electron to get to the octet. It doesn't care. It won't do a double bond. Anything in group 7 won't do double bond. So it's something we just happen to know. But let's say you didn't know that. Let's say it was very exotic elements, not like chlorine or something. How would you do that? That's why we invented the formal charge. So this is how we got what I showed you on the whiteboard. I can have what we just showed in the previous slide to look like this, or I can actually have a double bond between the C and Cl. So how do I know that this one is the one that I want and not the other two? Okay, so when I have, according to recipe, two things that are competing, we will need to discuss formal charges. And this looks very, very hefty, and I probably should have done some animations here to make it look a little more manageable, but let's go at it slowly. We're going to give each atom here, there's 4 of them, Cl, Co, and Cl. Each one of them is going to get a number, and it's going to be called a formal charge. And it's going to help us determine which one is going to be the correct structure. And I'm going to find here in green, the formal charge is going to be, for each atom, the valence electrons for each atom minus how much electrons I actually gave it. Okay, how do I know how many I gave it? This is how we get it. Assigned electrons are all the unshared electrons plus half of the shared stuff. Okay, let's go over this example and it will make much more sense, I think. Okay, let's look at Cl here. I'm going to go really slowly and you're going to get all of them, I hope. All right, so how many assigned electrons does this chlorine have? Well, it's all unshared electrons in red. So it's 1, 2, 3, 4, 5, 6. It's not sharing these, so 6. Okay, and half of the shared electrons. Well, it has 2 shared electrons right here, right? So half of them, 1. So 1. Okay. Carbon. How many unshared electrons do they have? 0. They're all shared. All right. So it is sharing 1, 2, 3, 4, 5, 6, 7, 8. Each bond is 2. So 2, 4, 6, 8. And I take half of that, so I have 4. Okay, and then oxygen. Let's see, it has 1, 2, 3, 4 unshared electrons, so 4, and then shared electrons. Well, each bond is 2. So 1, 2, 3, 4, and I take half of that. That's 2. So it's 2. Okay, so I have 7 here. 7 here is the same thing. 7, 7, 4, and 6. Okay, let's look here. Look, it changes a little bit. In this structure, I have 4 unshared electrons, and now I have 1, 2, 3, 4 shared electrons. I take half of them, so it's 2. So I have 6 here. All right. This chlorine is the same as this. Didn't really change. It's the same thing. I have 6 unshared and I have 1 shared. Okay. Carbon again doesn't change. It's sharing everything. It's still going to be 0 and 4. This oxygen did change from this structure. I have 1, 2, 3, 4, 5, 6 unshared, and I have 2 shared. I take half of that. That's the yellow and 1. So 6 plus 1. And so that's how I would do that. So here, this chlorine is the same as this chlorine. This oxygen is the same as this oxygen. It's the same type thing, okay? So I add this up and I have 7, 4, 6, 7. I have 6, 4, 7, 7. And then I have 7, 4, 7, 6. Whatever. So this is assigned electrons. I got to take valence electrons and subtract assigned electrons. Let's do that. Okay. So here, valence electrons for chlorine is 7. We calculated this to be 7. I subtract, and that's a 0. Here I have 4. Carbon has 4 valence electrons, and it has 4 assigned electrons. I subtract them, and I get 0. Okay. This one has 6. This oxygen has 6 assigned electrons, and it is also 6 valence electrons. So I subtract them, and it is also 0. This is the same, so it's 0. Okay, let's look at this one. All right, chlorine, we know valence electron 7. From here, I have 6. So 7 minus 6 is positive 1. Here again, 4. Carbon has 4 valence electrons. It has 4 assigned electrons. I subtract them. That's 0. Oxygen here has 6 valence electrons, but it has actually 7 assigned electrons. So it's 6 minus 7, and it's negative 1. Here it's 0 again. Here again, I get 0, 0, negative 1, and 1. So what I want to do, what is going to be my correct structure, is the one that has the lowest numbers of formal charges. So these are all zeros. That's right. Since I have ones and negative ones, and if I had 2s or 3s or something like that, I would shy away from those. So this is how you know that these are wrong. When the formal charges, you want to minimize them. You want to minimize formal charges. This is the best way to minimize it. Therefore, this is what it's actually going to look like. Okay. So there you go. You select the structure with the smallest magnitude of formal charges, and that's that.